always changes. Oh, yes. Okay. It's
How's it looking? How's it feeling with everything? Okay. Okay, y'all see the announcement? Miriam pointed out to me. And, I think it's because we took that extra piece of lecture and reviewed the polarity stuff. So I think we got behind a little bit. So I just extended a few days on the one that had been due last night to do Sunday night instead. Y'all, I'm always harassing Mark about doing all that stuff. You know you should. I know. But I gotta keep trying. Let's see. I encountered a comment last week, but oh no, I think it was Monday, about some of the math stuff and logarithms specifically. If you are trepidatious about logs and about some of the other math stuff, I still highly recommend going to the math science learning center. Yes, MSLC, right? Please do. Those folks love talking about math to you. They'll help, right? Y'all help, right? They actually do. They actually do. So if you get nervous about stuff in the maths, they can help with that specifically, but also the science side. Y'all do have some folks there. Go ahead.
Caleb, Jacob, Carla, I believe.
Caleb and Jacob also both had this course from me. Okay, so they're good ones to target. Caleb, Jacob, Ryan. Well, Ryan had Chem 1 for me, but no, I think that's right. But anyway, he's a good one to target too. So talk to them; they'll understand your pain, right? Yeah. So especially on logs, y'all. I know that we mentioned it this unit, but next unit and the one after, it's coming home, and you're going to be doing lots and lots of it. When we're going to compare rates, and I'm going to divide one rate by another, and I'm going to end up taking a logarithm and rearranging some stuff, and I'll say that like natural log of A over B equals natural log of A minus natural log of B, right? And so you'd be like, well, what kind of magic was that, right? So please go bone up on the rules of exponents, rules of logarithms, stuff like that. Make sure you can do those things. Make sure you know what I'm talking about with logs. So, right? See all this coming. Please no matrices for these guys, right? It was matrices for quant that boning up on. I guess technically, other than high school classes, college classes are prerequisites for quant that includes, because it's, you don't do matrices in college algebra or in pre-calc, right? Do a little bit, you know, brief, but not that much. Okay.
And then mostly that's been within your algebra.
I mean, I taught it when I taught high school algebra, so I taught matrices there. So that's why it's assumed that you would know how to do that.
Solve with your equations.
Yeah. Well, it's more than that. I mean, matrices are more than just solving. Yes, that is a practical usage of them, but that's not all they are. Okay.
The statistics. Yeah, in high school, I did a little bit of things.
Did you? Is that AP stats? Yeah. All right. Any questions before we get going today, y'all? Anything specific? Anything going on that I need to know about? Also would like to mention Allison's Discord. Is it?
Yes.
Okay, she has it up monitoring it now. I never see that. You say whatever you need to do that. And if you don't feel comfortable asking something, Allison will ask it for you. So, she doesn't mind stopping me as needed. And Allison just stop me as needed, even if they're not asking it, and you're pretty sure they should be. Okay. All right, y'all, reiterating this idea here, do expect to see one of these guys. So what we did at the end of class on Monday, how do you feel with it? Do you feel like you could do it? Tell me more detail than that, Mary. What is that like? Can you give me some more insight? What's confusing about it? Okay, do practice it more. That's a good point. There are multiple steps, multiple things to staple together, and sometimes that's a struggle. What else? Other folks got inputs on this guy? Feel like you could just do this? These are like 3 points on the exam. Good. Huh? It is? Okay. All right. And so practicing the number crunch, maybe if you got the concept level down and you're like, well, okay, I know what this segment is, and I got to add it to that segment, right? And if I do the sig figs thing, sig figs would only be a small portion of points if I apply it, okay? Don't forget your sig figs, they matter, right? And they'll matter upper level stuff, or the sig figs come back with a vengeance in one. Just remember that sig figs is the easy way out, right? The real way, the error propagation stuff, is even more complicated. Right, well, Chem 1, we talked about some of these ideas. So I wanted to rehash and see where we are on them. What is, I say, in the airbag lab, we were using six molar HCl. What's that about? What am I saying? Yeah, go ahead. Okay, yes, 6 moles of what? Hydrochloric acid, 6 moles of HCl in every liter of that solution. And I would remember I was saying, well, please don't use 6 moles. I didn't want you using a whole liter of concentrated strong acid, right? Yeah. Okay, and so that's getting the idea of what this capital M. Now we're going to get into another one, a lowercase m, an n, some other ones, talk through different concentrations. What do you remember from Gen Chem 1 about those different units? Like, how is this different from, let's say, 6 little m HCl? How are those two different? Anybody remember this? I promise it wasn't in your Gen Chem 1. It's in your textbook in chapter, I want to say 2, but it might be 3. This is not moles. This is molality. It is the second underlined word of their molality. What does it mean?
It's moles of solute for a kilogram of salt.
All right, so let's dig in a little bit and review those. Not hearing everybody like, oh yeah, this is good, this is old hat, right? Okay, molarity is by far the most common concentration unit we'll use in general chemistry, okay? And it's this capital M, the top one there, moles per, but I wanted to specify here, it is defined as moles per liter of solution. And I'm about to change that up on you on the next slide, okay? So digest that for a second. One of the things my quant students were looking at, Allison, this is an interesting thing that you'll see. We're making standards curves yesterday. They didn't have the idea of putting the solute. What does solute mean, y'all?
Salt.
Yeah.
That dissolve, solvent.
Yeah, it's the thing that's going to get dissolved. And solvent is the stuff doing the dissolving, right? Usually there's far more solvent than solutes. Sometimes it gets a little cloudy, but, okay, so moles of solute per liter of solution, what they were missing was they wanted to add, so we would make a 5 grams in 50 milliliters, 5 milligrams, in 50 milliliters of solution. They wanted to take 5 milligrams and then measure out very carefully and add 50 milliliters of solution to, of solvent to that, and that doesn't work. Because if you take 5 milligrams of solute and you add precisely 50 milliliters of solvent, you cannot guarantee that that's going to end up being 50 milliliters of solution. Because your solute might have added a little bit of volume to it. It might be slightly over 50 mils, or it actually can happen that your solute molecules interact with your solvent molecules and you get a smaller volume than the amount of solvent that you added. So they were confused by that. The way this one works is you would put your 5 milligrams into something that you can definitely control the volume of. We use volumetric flask usually. And then you add solvent until the total mixture ends up being 50 mils, right? So that was a really, that tripped them up a lot yesterday. I was surprised that tripped up my students. Yeah. So I wanted to reiterate that. Solvent, it technically can be any phase. And this surprises people. Let me find a good example. What do you think the shiny part of this thing is made of? Problem. So if I analyze that in the ICP, I would see nothing other than aluminum atoms. Is that what you think? Why? Or how about this guy? So the blade on that, right, is, well, what is that? So if I analyze, so that's iron, right? So if I analyze that on the ICP, I would see nothing other than Fe, iron atoms. Is that correct? No? Why not? Yeah, carbon, but also other stuff, right? So this, you'll notice, never polished that, but it's still shiny, right? Why? Well, mostly because of chromium atoms that are mixed into it. Not enough to make it chrome. It's not that shiny, right? But there are some chromium atoms, maybe some moly atoms to make it harder, stuff like that. That steel, it's a solution. It's solid, okay? But it's still a solution because the iron that makes up 99 point something% of the mass, right? The iron is the solvent, right? And the chromium, the carbon that Braden mentioned, all those other little bits in there are solutes dissolved in that iron matrix. Does that make sense? So don't get trapped into thinking that because in general chemistry, usually our solvent is going to be water, right? Usually it's going to be an aqueous solution. And yes, it will usually be an aqueous solution. But don't get trapped in the real world to thinking that's the only kind of solution out there, right? Gases, so air, so the nitrogen that you are breathing in right now, 78% of what you're breathing in is nitrogen. That's acting as a solvent that's dissolving oxygen, it's dissolving carbon dioxide. So you have a solution. It's a gas-phase solution, but it's still a solution. Okay? That makes sense? In orgo, you're going to use, oh my God, no, not water. Right? A lot of organic chemistry, you don't want water anywhere near your reactions. It will poison it. Okay? So you will use organic solvents, toluene, what else do y'all do? Cyclohexanes, what else do y'all use a lot? a bunch of not water, organic solvents, okay? All right, so now, back to this idea. Molarity, right, is moles, not grams, but moles of solute in liters of total solution, okay? I am sorry that it is this way, but they're not going to care that I'm sorry about it. They're not going to change it. Molarity, moles per liter of solution. Molality, little m, moles of solute per kilogram of solvent, not total solution. Okay? Now, the real reason it's different is because these units evolved over time depending on who was working on what. Okay? And so we're going to do a lab, is our terbutyl Monday? I think it is. I think terbutyl is Monday. We're going to do a lab where we're going to change the melting temperature of a solvent by adding stuff, solute, to it, right? And so people that were working on this area of chemistry, well, since you can't be sure when you're changing temperatures, you can't be sure of your volume so much, right? They didn't want to work in total solution volume. They wanted to work in solvent mass, because solvent mass is independent of temperature. Mass doesn't change when you heat it up. Volume does. So that's why the difference. But it is confusing. I accept that it's confusing. Now, if you have let's not say 6 like that, but let's say you have a 0.1 molar solution, right? That's only 0.1 moles in every whole liter of solution. Well, that's probably going to be really numerically close to also a 0.1 molal solution, at least in an aqueous sense, at least if we were talking about water as a solvent. Okay, so for dilute aqueous systems, numerically they're almost the same. If your solvent is not 1 gram per milliliter like water is, well, now I'm not so sure. Okay, and also if you get really concentrated, this is pretty concentrated. 6 molar is pretty concentrated. If you get up there and get really concentrated, right, then that might change things too. Your 6 molar HCl, actually I don't know what it would be in molal, but it might be significantly different from 6. Does that make sense? Probably in 5 somewhere. Okay, so far? Questions about these two? Yes.
Is molality?
Molality? Both molarity is all. Assume any chemistry exam you have from now on probably is going to include molarity. Molality, though, it will affirmative be on exam 1 in this course. And then, Allison, would I be correct to say that they're unlikely to see molality again until the final? Because we don't use it all that much, right? But I think your shorter term, your proximal question, yes, it definitely is. I am going to give you a molality question based on, like we're going to do in the lab on Monday, a question like that, where we're going to do colligative properties. Yes? Oh. 1 week from today? 1 week from today. Good so far? All right. I'm going to touch on normality here, but I don't think it's all that important. Or maybe it is. Yeah, normality. So normality, I just like throw it in there in case you see it. It may be going away. Have you ever had to deal with normality at all? It may be going away. The only time I see it, weirdly, nowadays, is with acids. So So a lot of times you'll see this capital N instead of a capital M. N as in November, M as in Mike. A lot of times you'll see the capital N up there, but weirdly, 6 molar HCl is precisely 6 normal HCl. Numerically, not different at all. However, 6 molar HCl, 6 molar sulfuric acid, H2SO4, because of that 2, would be 12 normal. So it's different if you have 2s involved and stuff like that. But since HCl only has the 1H on it, they're actually exactly the same thing. So it's weird that that's where I see it and there's no difference. But if you're working in a lab setting or something like that, if you've got old reagent bottles, you might see normality as a concentration. And that's all it is, equivalence. Equivalence per liter. Okay. This one, who was it? Miriam? Miriam, now, this was like fused in your brain, right? Okay, so mole fraction. And it's just, really, you can think of it as percentage of, right? So I said the air solution was 78% nitrogen, right? 21% oxygen. That's just a mole fraction. So if you count the moles of oxygen versus all the moles in the air solution, 21% of them, .21, would be my mole fraction. Okay, that's all mole fraction means. And now, which homework problem was that, Miriam?
Number 4 on 1. Yes.
Gastoid number 4. If you just use mole fractions, it was a heck of a lot easier than the other route that Allison and I tried to go. I mean, we got there, but it kind of filled up the board. If you just use mole fractions, like, yeah, just got it. Okay, go. So, yeah. Sometimes we do things like this just to make things easy. Okay? In geology, we use this all the time because a lot of times your solution in geology is a big old chunk of rock, right? And so mole fraction starts to mean a lot more then, right? So those are the concentration units that you should probably be familiar with for the exam. Note that normality, the one with the N, is not on there. You're not going to see it in this class again. Okay? Okay, let's see. Let's shift gears a little bit here and talk about kind of the physical chemistry underlying solutions. What's going on with solutions? Actually, before I do that, I'm going to go back just to make sure. It's still stressing. Is it? It looks like it is. And fine. Okay. Y'all remind me, please. What is this IMF? Not International Monetary Fund. That's a whole different discussion. That's not what this is, right? IMF in this context in Gen Chem 2, what am I probably talking about? Inter molecular forces. Why did I stress that inter? What am I? Okay, good. And what I want to talk about here is between solute molecules, also between different molecules of your solvent. Also, you can have IMFs between solute molecules and the solvent molecules. That's what I'm going to kind of explore here. So now tell me about that little blue, weird crossed arrow thing that I have up there. What's that about? Yeah, so there's a polarity here, right? And that's the direction of, and so we put that little cross on the arrow, kind of looks like a plus end of it. So that's kind of a mnemonic, but that's the more positive end. And where the arrow is pointing to is the more negative. Does that make sense? Now in this case, sodium and chloride are actually full positive and full negative charges. They're actually ionic, right? So the electron is not even shared like a polar covalent bond here. It's all the way over on the chlorine. right? Then solvent to solvent. These are supposed to be water molecules, okay? And they might be a little hard to see there, but later on you can download this PowerPoint. You can zoom in on those individual water molecules, and you can see that I have a new symbol on those water molecules, right? And Braden's going to be happy about my symbol here. You're going to have, ready? What's that? What's that?
I know that's what you use for density.
Oh, what is it in Cal 3?
Do we have the density function for whenever we're doing, central mass?
If I have this, F,
Yeah, we did do that.
let's say it's a function of X and Y, then you can have a partial, derivative of F with respect to Y.
Yes, and then you could, in order to fund the actual, I'm sorry.
We're not going to do derivatives. I'm just trying to target the partial. That's a partial, is what that is. It's a def, the lowercase def. So what that means, it's a partial. Now, going back up to number 1 there, remember I said the electron is all the way over on the chlorine, right? The electron is all the way over on the chlorine. It's not shared, right? But with the water molecule, that's not true. This is a very polar bond, but it's still a covalent bond. The electron is still shared. It's just that oxygen gets it most of the time. Does that make sense? And so we don't have a full positive. We've got a partial positive on the hydrogen end and a partial negative on the oxygen end. Okay? So you have this negative seeming region around the oxygen end of the water molecule, and you have this positive seeming region around the hydrogen side. Does that make some sense? Okay. Well then, if this water molecule here has got these little positive ends, positive-ish ends on the hydrogen, right? And this water molecule has got this negative end on the oxygen, right? What would those two water molecules see about each other? What would they, like, one water molecule is like, hey, I've got this negative end. Oh, you've got some positive ends. So what would that interaction probably look like? So there would be an attraction between the negative end of one of the polar molecules and the positive end of an adjacent water molecule. Does that make sense? Remember back to my thought experiment about the ice cube? That's your force that's causing things to happen, right? Either holding stuff in place or causing things to move. So you get these little vectors, right? And so you can get the positives attracted to the negatives, and you get these vector systems like this, right? You get these forces in between the molecules. Does that make some sense? Tell me.
So is that molecule just going to the bottom, right?
Yeah, it's attracted to so it's getting closer to, you should think of it, because remember that there are going to be other water molecules all around it, right? Because it's in a big solution. So but one end of is attracted to another end of the other water molecule, right? And that helps to orient them. And remember that water tends to be a liquid a lot longer than it should be according to its molar mass. And it's because of these forces attracting to each other, right? They're trying, not necessarily sink down, but trying to hold together. That's what the forces are doing. That makes some sense? Okay. Tell me more. What else do I need to talk about here? Because I'm about to change it. Yeah. All right. Well, now look, what I want to do is I want to take that model that we just developed here, and now I want to talk about it with the sodium and the water molecules. Also with the chloride and the water molecules. Okay? So now, what can you tell me about the sodium? It's all the way. It's not even partial. So yeah, it's like all the way positive, right? Yeah. Yeah. So my water molecules are they're envy, right? They got some positiveness and some negativeness, right? But sodium ain't. It's all the way positive, right? Okay. So what happens then when water molecules see it? Now, our water molecules before, the hydrogens were attracted to what about the other water molecules? The partial positive on the hydrogens was attracted to partial negative. And the partial negative on the oxygen was attracted to but now the partial negative on the oxygen can see a whole lot more positive things to be attracted to, right? Does that make sense? Well, and that's why certain things dissolve very well, is because those negative ends on the water molecule can see that positively charged sodium center and go get attracted to it. And they actually arrange themselves all around it. And so when you have a sodium ion dissolved in water, there's actually what we call a hydration shell around it. The water molecules are actually structured around that thing. Yeah, how many it is on I'm trying to say it here, but I'm not sure that's correct. You can actually tell how many water molecules start to structure around a specific ion, and sometimes it's more than one layer. Go ahead, Steve.
So since like the negative oxygen on the water see that sodium is like more positive, so they turn to it.
Yeah.
Likewise, why doesn't the like chloride ions see that Na is more positive? So they
It does. Okay, let me make sure I understand because there are two different things that I can immediately see that your question could be. One thing that you could be asking here that I'm thinking of is, does the chloride do the same thing with water molecules? The answer to that is yes, it does. I could have drawn this chloride with water arranged around it. They would be flipped over, and it would be the hydrogen ions pointing towards the chloride. Does that make sense? Also, I thought maybe you could have been asking, why does the chloride still not see the sodium? It does. It actually does. And so there's what we call a dynamic equilibrium, and there's a back and forth. But remember that there's a whole lot more of the water molecules around than there are other sodiums. And so you get an effect of, at some level, if you drop one NaCl formula unit into a whole, right, then you've got literally 10 to the 20, I think that's 10 to the 26-ish, a whole bunch of zeros, number of water molecules, right? So yes, it would still see it, but but it gets confused because there's so many water molecules around. Okay, fine. Well, what if we dropped one sodium chloride unit in, let's say, 100 water molecule units? There's still a lot more water molecules around than there are the sodium. Because there's only one sodium. There's 100. Does that make sense? But there's a limit to that. If you drop one sodium chloride unit into, let's say, 20 units of water, well, now I'm not so sure, right? We may have gone too far, and the sodium and chloride might still sit together. And we're going to actually calculate how much that is when we look at solubility product in unit 2. Does that make sense, Eddie? So yes, your intuition is absolutely correct. Yes, it does still see each other. The question now will be how much. Okay? Y'all follow that conversation? Follow what Miriam was asking me there? That was a really good insight. That's deep. Okay? Good. Then I could draw these vector interactions again, right? Just like we did within the solvent, or just like we did between the sodium and the chloride. Okay. Back in chapter 5, there was this little example, right? Now, this is back when we were doing the enthalpy stuff. So hopefully you'll remember calculating the delta H stuff or calculating the calorimetry stuff to see how much stuff heats up or whatever. Well, this was example 5.6. And it said you could actually use it to see the heat of solvation, right? What the delta H was when something went from a solid, what's our solid, did I say? Oh, there it is. Ammonium nitrate up there in the question, NH4, NO3. So you can actually see how much the solution changes in temperature by just going from a solid to a dissolved phase ammonium nitrate. Well, when it does that, you're generating, well, actually it's endothermic, so you're absorbing some heat, but now we can talk about what does that look like at the submicroscopic level? Where's the heat? Where are the joules of energy? Where are they going? Does that make sense? And that's what I want to look at now, is even though we did this problem back in chapter 5 in Chem 1, now we want to look deeper, zoom in on this problem and talk about, well, what's really going on? What's the crunchy level thermodynamics of what's actually going on there? Okay, y'all follow where I'm going with this? Follow my question? Okay. So what we'll do is we'll quantify each of these interactions. Okay, now these are the same three interactions that I had on that previous slide. So we've got the red, the solute interaction. So like the sodium interacting with the chloride, right? There's a certain amount of joules of energy associated with that. And then the water molecules interacting with the water molecules, there's a certain amount of joules of energy associated with that. Then there's a third different amount of energy associated with the sodium ions interacting with the water molecules, or with the chloride ions interacting with the water molecules. Does that make sense so far? So that's what we want to look at here. So molecular view, what's going on? You have 3 steps. The first one, you've got to take your solvent, let's say our water, okay? You've got those forces holding the water molecules close to each other, right? Well, then we must be applying some energy to pull them apart, right? Because there's a force holding them together, we're applying energy to pull them apart. Make sense? Okay, cool. So that's our first step, and our delta H will necessarily be endothermic. Here we've got to apply energy to this, right? So a positive value of Q, a positive value for delta H here to pull those molecules apart. They're trying to hold together. So we've got to apply in some energy, okay? Then, same idea with our solute. Something is holding that solute together. To pry it apart, we need to apply some energy, right? So again, our delta H is going to be endothermic. We've got to apply in some energy. Make sense so far? Maybe? Okay. Well, where we get it back then is step 3. Now since we pried apart our solvent molecules and we pried apart our solute molecules, now we let them get together, right? And they come back together, and this is going to be an exothermic process. But be careful, don't get ahead of me yet. I'm only here saying that step 3 is necessarily exothermic. Okay, only step 3. Step 1 and step 2 are necessarily endothermic. Step 3 is necessarily exothermic. But now I need to balance those. Right? If the total amount of energy that I put in endothermic to do step 1 and step 2, if that total amount that I put in is greater than the amount I get out in step 3, right, then my overall solution process would be endothermic. However, if the total amount in step 1 and 2 that I put in is less than the amount I get out here, then it will be an exothermic solution process, solvation. Okay? And so that's what you can look at with that. Our total delta H then is delta H for step 1 plus delta H for step 2 plus delta, you just add them all together. Because remember, we can't actually see step 1 happen. We can't actually see step. All we can see is this delta H where all 3 steps happen added together. What we'll try to do then is you can try to do it with different things. You try to do it with sodium chloride. See what that does in water. Then try to do it with sodium, let's say, bromide, right, in water. And then maybe do lithium chloride and lithium bromide. And then you start to try to take the maths apart and make it all make sense. Probably use matrix, right? With this one, specifically,
Yeah, that one.
necessarily exothermic, yes, negative delta H. Yes. That makes sense? But only step 3, guarantee is, not the sum. The sum, it depends on how step 3 relates to steps 1 and 2. And here is actually the comparison, right? I think a lot of times this just gets presented in the book. Here it is. Cool. Hope it makes sense to you. Go. And I wanted to take it apart a little more than that. Okay, look. What is this saying? This is saying if the absolute value of these two is less than the absolute value of this one, right? Then what? How would you fill in the statement? I agree. It would be exothermic. Does that make sense? And then number 2 here, if absolute value of H1 and H2 put together is greater than absolute value of H3, then endothermic, right? And this is maybe a new term for you that I'm about to use here. Okay, right? Y'all use this? It's not misprint. That's on purpose. Okay, sorry, I'm going to say it a certain way. This one says, if the absolute value of the sum of H1 and H2 is greater than the absolute value of H3. This one says, if the absolute value of H1 plus H2 is a hell of a lot greater than the absolute value of 3. I'm sure that's not the official definition of that term, but that's what it means, right? It means a lot greater. If this is a lot larger than this one, then you should think, well, that one is spontaneous, okay? So then that's foreshadowing for you again, and we're going to talk about spontaneity in the next unit. No, that may be in unit 4. I think it's in unit 4. But it's not. All right. Good so far? All right, I'm going to shift gears a little bit. All right. Let's imagine thought experiment, right? That you have a kid. Okay. Now, this kid is kind of precocious, right? And you've got your girlfriend's favorite glassware, china or whatever. Okay. And kid has drawn smiley face with a Sharpie on it. Y'all know how hard Sharpies are to get off? Right? Kind of like permanent, right? What do you do? Spray with water? Well, wait. Like what? Like, what would you use on Sharpie? Yes.
Alcohol.
So alcohol, if you scrub it hard, you might do some good with Sharpie. Let's say it's not China. Because that when China you can scrub pretty hard, right? But those say it's plastic. Right? It's plastic, and you scrub it real hard, you're going to start scratching it, right? Remember, it's her favorite. We don't want to, right? So what else do we do? What do we try to do? No. It's mostly alcohol.
You cover the entire thing, sure.
Yes, actually. But where I was going to go with that is this is a little life hack. The best thing to get Sharpie off is Sharpie. So if you've got Sharpie on something and you need to get it off, and you need to do it quick, have your little paper towel ready, color over it with Sharpie and wipe it off immediately. Right? Why is the ink in a Sharpie, why is it liquid when it first goes on? Because it's dissolved in something, right? Something that will dissolve Sharpie ink, okay? It's a solvent called xylene. Sharpies, the solvent involved in Sharpies is xylene. Xylene is an organic chemical, hexagons. Get ready for hexagons, they're coming in order, I promise, right? Those are carbon, 6 carbons around it, and it's got 7 carbon here, and then either here, here, or here, it's got an 8 carbon. There are 3 different flavors of xylene. So that's xylene, right? Definitely not water at all, totally non-polar, right? Because all those are carbons and hydrogens. There's no polarity to that bond. So you need a totally non-polar solvent, apparently, to dissolve the ink in Sharpies. Now, it turns out these rings with this alternating double bonds that I've done like that, it's called aromatic rings. And aromatic rings can actually help dissolve things with aromatic rings. And so a lot of dyes, like the ink in a Sharpie, have those aromatic rings like that, right? Well, then it's good to have something else that's got aromatic rings to help dissolve it. So you can actually, I've done this actually with plastics even. You can just color the Sharpie and wipe it off real quick. Sometimes it takes 3 or 4 times, but it actually works. And then Mark is right. You can come back and polish it up with alcohol to like clean the spears off of it at the end, and that helps too. Okay? Make sense? All right, that was all kind of thought experiment because the principle that we talk about in chemistry is like dissolves like. So if I want to dissolve a non-polar thing with these aromatic rings, I want to use a non-polar aromatic solvent. If I want to dissolve something like gasoline that has a lot of straight chain carbon-hydrogen bonds, but no polarity whatsoever, use something else that has straight chain hydrocarbons with no polarity, 0 polarity. Does that make sense? If you want to dissolve, I told my quant students this because they think that we put sodium hydroxide solutions, and you remember doing the burettes where we do the titration, you get the pretty pink color? Well, they have their own assigned to them burettes, and they put sodium hydroxide solution in it, and then they were cleaning them, and I watched one of them clean them, I'm like, why are you using alcohol? No, because I needed to clean it. Well, actually, the alcohol makes it worse, not better in that case. Because sodium hydroxide, we're going to learn this in Unit 3, is ionic or very, very, very polar, right? So a non-polar solvent is not good. You want a polar solvent to dissolve ionic or polar things because like dissolves like. So actually, with sodium hydroxide, the best thing to dissolve is just water. So I was telling them, just use distilled water. That's better than your alcohol in this case, because like dissolves like. Does that make sense? Okay. Hey. Those are little structures that you'll see a lot in Forgo, right? The one on the left is the kind of alcohol that you might get involved with on a Saturday night. The structure on the right is methanol. Please don't drink that, it's wine. Okay? So 2 substances with similar intermolecular forces. Similar here, I mean polar, non-polar, right? Hydrogen bonding. Those intermolecular forces, if they have similar ones, they can interact better with each other. Non-polar molecules, soluble in non-polar solids. Like carbon tetrachloride dissolves well in cyclohexene. That's benzene. Cyclohexatriene, if we named it correctly, nobody does. But polar molecules, though, are better dissolved in polar solids. like ethanol in water, right? Anybody know what, if you go to the liquor store and you're looking at, what's your favorite liquor? Okay, so it's not 19. Miriam better not have a favorite liquor, right? No, okay, good. What's yours? What's your mom's favorite liquor? It's what?
Fireball.
Fireball. All right, so there will be a thing on the label that says Fireball is, I think Fireball is 80 proof. Not sure. But y'all know what that means? 40%. It's weird because it's double the percentage. So 80 proof is actually 40% alcohol. 190 proof Golden Grain, right, is 95% alcohol, right? Well, what's the other 5%? Water. Mostly water. Why did I be sure it's water and not toluene? Because the molecule on top left up there, it's quite polar. That's an ethanol molecule, right? It's polar, and so the good thing to dissolve it is water, right? You can get some neat interactions later after you turn 21. Try stuff like ouzo. It's a Greek liquor, and you'll see they like to pour it over ice and it'll immediately turn cloudy. And that's because of solubility limits. So some of the stuff in it, some of the non-polar stuff in ouzo will drop out, become cloudy when it hits ice. Neat stuff you can do as a bartender. Another thing that sometimes is not intuitive to people, I say like this dissolves light, and polar molecules do dissolve well in polar solvents. However, also ionic compounds are like, think of them in this case as being super duper polar. And so they also like to dissolve in polar solvents, okay? Like sodium chloride. Sodium chloride dissolves well in water. Okay? Sodium chloride actually dissolves very, very poorly in organic solvents. So a lot of times you can use an organic solvent to separate out your salts. This happens in Orgo lab all the time, right? What's the drying thing? They use calcium sulfate, I think. And so they'll use it. It'll grab all the water molecules, right? Because light dissolves light, so it's ionic, and it'll grab the water molecules. Well, that way they're no longer in your organic solvent, because remember, a lot of times in Orgo, water is poison. So. All right, cool. Nobody has any fancy water bottles that I see. Anybody drink any of the fancy stuff like the electrolyte label? What's the advertising that they use? What do they advertise to you guys? Like super electrolyte, like that. Yeah?
Right, yeah.
Do y'all know the story of Gatorade? What's the story of it?
Basically,
Yeah, do you know any more specificity to that? We think it was 1965, right? And so football players at a certain university, right, were really hard charging in the first half. And then the third quarter kind of slowed down. And the fourth quarter, they were just drug out and wasted, right? Because they were sweating so much. And this university happened to be in Gainesville, Florida, right? And it gets really hot and humid down there. And so they were sweating a lot and they were losing a lot of electrolytes. And so they actually went to the chemistry department at UF, right? And they said, hey, could you help with this? And chemistry professors were like, oh yeah, we can help with this. And they created a solution that would replace electrolytes in those players, right? Apparently UF has a mascot, it's the who? The Gator, therefore Gatorade. That's, yeah, okay. So it was all about the electrolytes, right? I think it was 60, I'm not positive about the year, but it was 60 something. Steve Spurrier was ordering. So what are those things, those electrolytes? What are we talking about? Y'all talk about this all the time in biology, right? Go ahead.
Electrolytes are ions.
Is it just any random ion?
It's mostly solid.
Wait, what did you say differently then? I'm going to dig into what you just said. Salt or ion or both?
Yes.
Yes, both. Okay, so it can be any random ion. Okay, let's take the word apart. What does it look like is in this word? Electro, what's that probably going to be about? Okay, good thoughts? About electrical conductivity. If you have absolute, I do not recommend you do this experiment, by the way, please do not. But if you had absolutely pure water, right? This is still a thing that they worry about teenagers dropping hair dryers in the tub. Is that still a concern?
Kids make jokes about it.
Okay, it was a thing in the 80s. People actually died. 80s as well. But anyway, so you drop your hair dryer in the tub with you, right? You get electrocuted, yes? Because water will conduct electricity, right?
Kind of.
Turns out, absolutely pure water will not conduct electricity. So I actually have a machine upstairs to make ultra pure water. Well, it did before somebody broke it, but broken right now. But well, anyway, but it would make, so Brandon, you've had physics or currently in physics? So what are ohms? Resistance, right? And so the higher ohm value that you have, right, the more resistance you have. So our nanopure system up there would monitor itself and it would get water down so that it was so pure that a centimeter of water, like electrodes separated by a centimeter, would have 18 million ohms of resistance. That ain't conducting, right? Does that make sense? No, Miriam, tell me. Okay, so tell me what an ohm is again.
It's a measurement of resistance.
So like, Miriam, have you plugged stuff into the wall, right? And that's dangerous, yes? I'm going to shock you when you plugged it in. Yeah, because that insulator, the coating on the cord, has a high ohm value. It's spelled OHM. It's usually an omega. It's kind of like a O, Greek O. And that describes how much resistance it has to electric flow, right? So pure water, if you have truly, truly pure water, we're going to set this system up here. We're going to plug it in. We've got one cord stuck down into the beaker. I don't know why you would do this, but okay. And go into the light bulb, right? Absolutely pure water, no electricity flow, does not conduct electricity, right? Does that make sense? If you have a strong electrolyte, salt water, almost as good as copper wire. It conducts electricity very well. Okay? Does that make sense? If you have a weak, I think it might be hard to tell from the graphic there, but what they're trying to show here is with a weak electrolyte, yeah, it's conducting, but that bulb is not very bright there. So you're getting a little bit of conduction is what they're trying to show here. Does that make sense? And this is analog. It's not like yes strong, yes weak. There's a whole range of in between. Okay? Does that make sense? Now the reason I don't recommend you try the dropping like making a tub full of absolutely pure water, getting in and dropping your hairdryer. And the reason I don't recommend that is because it's not going to be pure water. As soon as you get in it, you're the solute. It's not pure water anymore, and it will in fact conduct electricity because it's dissolved a little bit of you. Okay? Make sense? This is important to know too. Strong and weak, when we get to unit 3, we're going to talk about acids and bases, and we're going to use essentially this same idea. A little different than you use strong and weak in general usage. Strong means that essentially all of it is dissolved, okay? So if you have sodium chloride up to a limit, let's say we don't have enough salt in our water for it to be crunchy, okay? So it's just salt water, right? Well, essentially every sodium ion is surrounded by water molecules, and every chloride ion is surrounded by water molecules. I was talking to Miriam about that, right? There's so many water molecules around that is totally broken up, right? So that's a strong electrolyte. A weak electrolyte, on the other hand, means that some of it is broken up, but some of it is still stuck together. Okay, so I wanted to cement this idea in using electrolytes, strong and weak. We're going to use that same idea later when we talk about strong and weak acids. This same model of what strong and weak means is going to matter there. It depends on the chemical itself. Okay, so just taking the chloride system. If we take sodium chloride, again, not past our limit, just up to a certain limit, and we'll put it in water, it's essentially all of it. Okay? But take calcium chloride, CaCl2, right? And I put it in water, and if I look close enough, I can actually find intact some CaCl2 stuck together. Also, I could find some that is Ca with one Cl stuck. That happens too, because calcium chloride is not as strong an electrolyte as sodium. And there are others, plenty of others that are in between. Does that make any sense? Especially in your world, when you're looking at biologic systems. Okay, so you're going to talk about a lot of ions attached to protein structures, which are essentially supermolecules. Okay, and how much dissociation energy they have determines how strong an electron. So we know that the water and other polar molecules will be attracted to the ions, right? And so now we're gonna staple a name to that. This electrostatic, that's just the forces that we were talking about, our arrows, right? Our force arrows. That attraction between the ion and the molecule is called, and we used before, did we use the term dipole-dipole interaction? Right? Well, now we just staple the name ion-dipole interaction onto it, right? It can be used the same way. It's just the sodium doesn't have a dipole, it is a pole. It's kind of a monopole, right? And so it's just positive. Make sense? And we call it dissociation when the sodium chloride goes apart. Here's a little graphic of it. So you can see this is KCl. Now here we're limited by how many water molecules are available. But we have this KCl, the purple and green, this KCl crystal. See the regular patterning to it? That's what makes it a crystal, right? So we have this KCl crystal, and then we've got these water molecules coming in, this positive in on this water molecule. Oh, look, I saw a chloride. I'm going to try to snap to that, right? And then they start to pull them apart, start to pull little pieces of ions off of it. This is the process of dissolution. Sometimes I will say solvation. Solvation is technically forming that sphere of water molecules around it. But it's the process of dissolution of the potassium chloride crystal. Does that make sense? They're still not talking about stuff. Okay. This next piece, this goes to what we're going to do in lab on next Monday. Yeah, Monday. Oh, I'm off by a week.
And then the next is the.
Thank you.
Freezing.
Okay, freezing point depression will be colligative properties. All right, got it. So 2 weeks from Monday, or 1 week from Monday, 2 weeks from last month. We got the next. I think I made that more confusing than
Yeah.
you. Sorry. Not the coming up lab, but the one after that, we'll do this. There you go, soon. Let's see. So, a couple of weeks ago, we had that horrible cold snap. Did we? Yeah? Who's got to drive over a mountain? Who has to? You do? Where are you driving from?
Well, I'll have to drive over, I'll have to drive down.
Which one you got to drive down?
Sand Mountain.
Sand, okay. So you're coming down off Sand Mountain. Okay, cool. So, do they do anything to the roads during that horrible winter weather that, like, I was calling my friend from Pennsylvania and said, Frank, you need to come down here and get your weather. It's in my yard drunk. So, yeah.
The first day, I didn't think of anything, and then the second day, they had like those big old things
Those big old things that,
that like put salt.
oh, well, wait. Why are we putting salt on our roads? What's that about? What's going on with that? Yes.
The salt on mountains. Because the solid ice to turn back into water, it lowers the freezing.
That's what I'm after. Now, last piece. Say that last piece again, loud.
Lowers the freezing point.
It lowers the freezing temperature. So it turns out that salt water freezes at a colder temperature than pure water. And because chemists love doing this, we can set it up in a graph and make a straight line and calculate that. Okay, does that make sense? That's what we call a colligative property. Got another piece of what colligative means here. Which salt do they throw in your roads? Which salt would we use? Don't know, don't care. That's important for colligative properties. It doesn't matter. All that matters is how much stuff is dissolved, not at all what the stuff is. So when we do these graphs, all we're going to care about is how much total dissolved load there is, not the identity of the stuff at all. Does that make sense? So one of the things that's happened before when we run the experiment is people get bad data. We had these test tube things set up and use a paper clip and keep stirring it, the turbulent alcohol to watch it freeze, right? And what I noticed was that in moving that paper clip up and down through that rubber stopper, they were sawing off little bits of the rubber stopper. Well, that's stuff. And remember that our properties don't care what the stuff is, only that there's stuff there. And our turbulent alcohol is actually partially polar and partially nonpolar, so it would dissolve some of the nonpolar rubber stopper also. And so it was changing our values. So we'll have to talk about some details of how we can get around those errors too. Okay? So does that make sense that it doesn't matter what? Just that something is dissolved and how much of the something there is. Yes? Maybe? Brandon, are we about full there? Okay.
Yeah, I'm fine. Okay.
Please do, yes.
So like the main idea in the OChem lab is synthesizing something that you get in. And sometimes, we're not perfect with how we do that. And we're gonna get little imperfections in our final product, which we call impurities. And one of the ways we test for how pure our synthesized molecule is is by checking usually the melting point of it, depending, I guess it depends on what it is. But normally in OChem, you get like a powdery substance that you can melt and see when it melts.
Yes.
And so the impurities inside of that will sometimes shift that melting.
Or broadly.
Yeah, so that's like a real world example of this sort of stuff.
Yeah, if that property were important enough in organic chemistry, it almost seems like we would even maybe created a special machine to look at that. melt temp.
Oh, yeah.
Yeah, it's
I
just,
thought it
it's
was
called melt temp.
about the, one Austin.
Oh, man. Hey, we actually have machines that we pay money for, so you can carefully watch what the melting temperature is of your organic, because you're gonna change it by your.
Actually, I mean, if y'all are gonna take okay.
Most of, I think everybody, let's see, Brayden doesn't have to take it, but all your biology needs, you gotta take it. Yes.
So you will get to experience that. You will see if you have a pure, synthesized product.
Yep. All right. Some colligative properties, not an exhaustive list, there are many of these, but some that we're going to discuss are like vapor pressure lowering, boiling point elevation, freezing point depression, that's the one we're going to do in lab, or osmotic pressure. Now, one thing that I want to point out here, just to lock it in early, look at what's happening. Boiling point elevation, freezing point depression. Okay, so if I take salt water, it's going to freeze at some temperature lower than 0. But it's going to boil now, because it's salt water, at some temperature higher than 100. It's like they go opposite directions. Does that make sense? Yeah. Yeah, one of the things I'm worried about this, also, do you cook much? Okay, yeah, fair, yeah. So like, one of the things I've often seen, in cooking pasta, you want to boil your pasta, right? And a lot of the advice out there is to like put some salt in it so that it boils more easily, and that's wrong.
That's not right.
That's backwards. Well, what's the salt for?
But it's to season the water.
Okay, yeah, and that makes sense, and I usually use garlic salt because of that, but yeah.
And also, it cooks at a higher temperature.
Ah, so that makes a lot of sense. Murph, say that again. Now you're telling me, this is new for me. I love it, thank you.
Now the water is boiling at a higher temperature.
So I can get my water solution maybe to 102 C instead of 100 C. Okay, that makes a lot of sense. So it's not to get it to boil more easily, it's actually to make it harder to boil so that the temperature is higher. That makes a lot of sense. Thank you.
You should use garlic salt for pasta, that's genius.
Okay.
That's why.
Oh, wait, I got another one for you then. If you like your pasta, okay. My wife was like, wait, why have I never thought of that? So like I cooked spaghetti the other night and so I made a homemade sauce and stuff. But then I got the spaghetti noodles out, put on her plate, right? And I put Parmesan cheese on it. And then put the sauce on it so that the noodles themselves are good. Right? Does that make sense? Now in my case, I'm weird, so I put Parmesan on mine and then put about twice that much red pepper on mine, but that's just me. So, anyway, I love my red pepper. So, okay. I like black pepper too on different things. Usually black peppers for gravy, eggs, stuff like that. Stew. Red pepper, that. Pretty much everything. So, yeah, do you like Thai food? Okay, you get it Thai hot?
Thai spicy stews.
It is, isn't it? Yeah. We went to, the, Thai place in Fort O. Have you been to that one?
I have heard it too.
Oh, what is that called?
Is it like sweet rice? Or is that the-
No, that's further up. That's in Chattanooga, right?
I'm gonna go on a tangent.
Go ahead.
A lot of the Thai restaurants in America are actually put in place with Thai food.
Are they?
Travel. It's really interesting.
That is nice. Okay, that makes a lot of sense. Huh. I went in and so I asked for, can you go ahead and make mine hot? Okay, she said, you want it Thai hot? Like, depends. Where's your chef from? Looked at me, she said, it's from Bangkok. I said, yes, it's Thai hot. She's like, what? So, well, if you said he was from Phuket, I do not want Phuket hot. And she said, oh, you know Thailand. And I'm like, yes, I spent some time in Thailand, right? If you get Phuket hot, it might catch fire on the plate, but okay. All right. I love tea. I did not know that about Tiger. I had suspected about the Chinese government, but I didn't know that
There are
about
no Thai
Tiger.
restaurants. Burmese.
A lot of them didn't make tea though.
I don't know.
All right. If we were doing liquid vapor equilibrium, do you remember me using that terminology, equilibrium? What did it mean? The equilibrium there mean? There's like a bulb, and there's a vapor coming off of it, and it's like a pressure gauge, right? You know, what is equilibrium mean? Had to do with the amount of molecules in one thing versus the amount of molecules in another
The
thing.
amount of molecules. Getting out of the liquid and entering the gas, you can also found gas molecules.
And so you were getting a balance of the number of molecules going one direction and the number of molecules going the other direction. That's an equilibrium idea. Okay. Now I'm going to start to use a circlate here, the two-directional arrow. Okay. You might not have seen that in Chem 1. If you had my Chem 1, I probably drew it half the time accidentally, right? So, but that's going to mean a specific thing. It's going to mean an equilibrium process. Okay? And so if we have an equilibrium established, that's going to matter, and it's going to matter for a lot of the math coming up in Unit 2. Okay? But here we're going to talk about vapor pressure. All right, now what's vapor pressure? Take me back, please, to, I don't think it was Stoid, I think, which one? Was it gas Stoid that had your problem in it? Okay, that was gas Stoid? Okay. The gas Stoid homework. Remind me, y'all, about partial pressure idea. What's that about?
The amount of pressure to gas.
One particular piece of the gas, one particular flavor, like the water. So the water that you're breathing in right now has a certain partial pressure all its own, right? Okay, and so you can establish, if you open this, we talk about, I've used this example many times. You open this, right, and you leave it here open in the room, and you come back and check on it in a month, right? Has the water level changed? Probably. It's probably evaporated down. Does that make sense? But one of my favorite environments on the planet, if I take this same thing into a cave with me, okay, and I open it and leave it exposed to the atmosphere for 2 months, it probably won't significantly change water level because the air in a cave is pretty much already saturated with as much water as it can. So even though I'm not saying that none of your water molecules would evaporate, they would. However, there would be an equilibrium process and just as many water molecules would go get in as came out. There would be an equilibrium established. And so you get an equilibrium wherever your conditions are set. Does that make sense? Okay. Do y'all look at relative humidity in the weather ever? Does anybody have anything they do that they care about relative humidities? Nobody does any gardening or fire, you're like making campfires? Y'all, there's a reason I mentioned that.
I did exactly as I was told.
And what happened? Okay. So you have to be worried about when you're making a fire, how dry things are around you, right? We've had some severe fire weather, right? And a lot of that is related to our relative humidity. When relative humidity is low, that means that the air is not yet at equilibrium. So it's going to suck some water out of everything, including really large pieces of cardboard.
Okay.
So that's an equilibrium process, right? And so it will be established. Now, if you take Murphy's piece of cardboard into the cave and leave it, it will actually absorb water from the atmosphere. It won't become like soggy, wet, terrible looking cardboard stuff, okay? Because it depends on an equilibrium process with what your percent humidity is in the air. Does that make some sense? I'm gonna channel that idea then coming up here. So this is the idea of vapor pressure. Okay, this is a graph. I'm not trying to build a pentagram here. This is just okay. So all right, it kind of looks like that. But anyway, so we get pressure, right? And so we think that we can make this graph. We're all about making our graphs, right? And about the x and the y, the mole fraction, and setting up a vapor pressure between two end members. So we'll have this much vapor pressure if it's all this material. We'll have a different vapor pressure up there if it's all material B, right? And if it's somewhere in between, that piece system up there is the tie line between those two components' individual pressures. So if you actually took this graph and sat down with it, just draw on it. So what I'm doing here in red, so this is the YB line, 0% here and 100% or 1.0 over here. So this is the red line, right? And so if I look at how high this is right here, that was supposed to be at the very top of that story. And then also look at that right there, right? And I add the red and the blue together, I would get that top line. Does that make any sense? Because the sum is the different components, right? Just like our problem in the homework, it is the Dalton's law, the sum of the components. Does that make sense? And so in theory, we should be able to find a straight line, a linear system tying 100% A on the left to 100% B on the right, and have a linear relationship between the two to try to determine what our composition of our mixture is. Does that make sense? In theory. In practice, it never works like this. It's not a straight line. It's usually got a eutectic and a lot of other things. It's really complicated. But in theory. Okay? All right. So hopefully you've got what you need. Yes. To go forth on the homework, and then we'll return to the other. Start studying hard, right? Oh, how are you on cheat sheets? Remember the cheat sheet thing? Please remember your cheat sheets. You don't want to show up to exam one without one. Okay? It will hurt. And I don't know what else is going to say here, but I would encourage y'all sharing with each other too. If you come in right before the exam and copy somebody's cheat sheet, that's going to be better than not having one. Okay, but it's not going to be as good as you creating one and putting on it what you want. Okay, so I highly recommend you spending some time ahead of time to make it yours.
And we also have an extra SI session
Oh, yeah.
Monday at 5 p.m. So directly after your class. Some reviews will be like a big study set. But just let me know what y'all